Hi again. Okay, want to go ahead and get into the first module here. So module 1 is going to be dealing with just basic looking at data, reading it into R, very gentle, explaining random variables and statistics. So you had a probability class before this with Dr. McDaniel, and you should have some kind of background from there, but I'm actually assuming that you're coming from the ground up. So we're going to work very patiently through this, and I hope you all have a good learning experience. So this module introduces concepts of random variables, introducing you to our statistical software, which we use throughout the course. It's a free open source object-oriented language that effectively performs statistical analyses. So that's key here. It's free. SAS, for example, is for companies, I think it's $60,000 a year, which is kind of outrageous. So this is a free software. It's very transparent. Everybody releases things. And I think this is going to be the way of the future as far as statistical software between this and Python. So we're going to work in R, and it's going to set you up for long-term success. And I think, in general, right, outside of statistics, having some kind of coding background and ability is a skill that's going to, improve your job prospects for the rest of your life. So I hope that this course gives you those kind of things as well. So statistical analysis involves collecting a sample of data to draw inference about random variables. In the image shown here, so this is the image here, the researcher is interested in the average height gain for 7-year-old students. So this is some students, Greg, Jared, Diane, Jenny, Charles, and these are their height gains in terms of inches. So in 1 year, Greg grew 2 inches. In 1 year, Jared grew 3 inches. In 1 year, Diane grew 4 inches. In 1 year, Jenny grew 5 inches. And in 1 year, Charles grew 6.5 inches. And you can see this I here, this is just the index number. So these are the observation numbers. The researcher goes and finds heights of 5 students and records their height at age 7 and 8. They record their names and height gains. You could use this information to estimate height growth. So, based on this, right, this is 5 together, 9, 10, 0.5. So roughly on average, these students are gaining about 2 inches per year in height. Upon the completion of this module, you'll be able to describe concepts related to random variables and list real-life examples of continuous and discrete distributions. You'll be able to perform basic descriptive statistics and graphs in R. You'll be able to understand mathematical notation related to statistics, including means, variance, and products. So to achieve these objectives, the first thing you'll do is watch this video, which is the one you're watching right now. You'll take the first module quiz. You'll download R in RStudio, so make sure you go and do that. Again, try RStudio first. It may give you the option to download R. Otherwise, you'll have to download R afterwards. And then you'll watch the second module video. You'll watch the third module video, and you'll actually run R code for the lectures and follow along. So what I'd like you to do is I have R code here. I would like you to just follow along the lecture right now. And then later on, after we're gone through all the lectures, pull up the R code and actually run it line by line and see what's going on. So you'll have that experience. The code's already there for you. You don't have to do anything to it. And you'll have that experience of actually stepping through it and making sure that it works, seeing it work. Complete the homework assignment. So let's go to the module 1 resources. So this is going to be updated after I recreate this video. Here are the lecture slides. You can grab these lecture slides down at the bottom. I have the R code up here too. You can see it'll pull up like a new window like this. If you want to use this in R, all you need to do is just copy this, and you'll plop it down into RStudio, and then you can run things. So we'll look at all that later. I just wanted to kind of show you what these resources look like. Okay. So, introduction to statistics, module 1 lecture run. Okay, what is statistical analysis? So just like that example, right, where the researcher wants to know about height gains and he goes and collects height information on a bunch of different students. The goal is to use sample data, right? Because they could go to the school down the street, they could go to a school in Wyoming, they could go to a school wherever. You're going to get different heights from kids in those different areas because they're actually different kids, right? They're going to have different growth patterns and things like that. So statistical analysis, we go collect samples, whether it's from here, Wyoming, whatever, and we try to answer questions about the population as a whole. So we try to go collect information on 200 students, something like that, and get some kind of idea about what the average height gain really is for students of this age. So these examples, right? Do heights of 7-year-olds increase by over 2 inches on average? Does a given treatment decrease death rates? So anecdotally, right, we have vaccinations for COVID, for example. And, we saw that taking the vaccine, COVID vaccine, greatly reduces your risk of death from COVID-19. And there's lots and lots of studies backing that up. So, I mean, there's really concrete, profound information on that. So just be aware that research was solid and done really well. Another question you might want to ask is, are obese patients more likely to get cancer? Okay, so you could look at obese patients and non-obese patients and look at the cancer rates. So you actually go collect that information. You can determine these questions by getting sample data. What is a sample? Okay, again, a sample is just collecting this information. So for example, height increases in 7-year-olds before turning 8. If I want to know the average growth of 7-year-olds, I can go collect a sample down the street and see if it's bigger than 2 inches, for example. I can record the heights of children at their 7th and 8th birthdays. And this is going to be the first math. So we're going to have some math here. I want you to be very not scared of this. It's not a scary thing. So here XI is going to denote the height gain of the ith child. For example, XI equals 25. That would mean that they grew 25 inches, which is probably not plausible. But, I here is an index. So if you have 5 kids, you're going to have an X1. That's their first height growth. You're going to have an X2, an X3, and an X4, and an X5. One for each child. So here's an example here. This is going back to that same data. Let YI denote the name of each child. So this is just another variable. You can use whatever you want. You can use W's, Q's, C's, A's, B's. It doesn't matter. The thing is you have to define what you're using whenever you're saying here. So I'm saying I'm using YI. It's the name of the child. Could have been a Z, could have been a Q. Does not matter at all. Okay. So here, right, Y1 is equal to Greg. Why is Y1 equal to Greg? This is the index number here, and this student's name is Greg. And X1 is equal to 2. Why is X1 equal to 2? Because that student gained 2 inches of height. AKA, what this data says, a child named Greg grew 2 inches from 7 to 8 years old. So Y3 here, the third entry is Diane, and X3 is 4. So what does that say, right? A child named Diane grew 4 inches from 7 to 8 years old. So let's just continue to walk through it. So Y1 is Greg, Y2 is Jared, Y3 is Diane, Y4 is Jenny, Y5 is Charles, X1 is 2, X2 is 3, X3 is 4, X4 is 1, and X5 is 0.5. So I'm just defining these variables, and we'll use these later on. But XI is going to denote the height gain of the ith student. So it could be X1, X2, X3, X4, X5. Okay. Okay, so this is math. Do not be afraid of it. So here is something that you can compute on average, right? Maybe you want to compute the average height gain, which we did earlier, which was about 2.1 inches, right? So what this is X bar. This will be the sample mean. This is a summation is what this is called. So this is a summand. I don't know if you've seen it already. All this does is represent that you're summing over I from I equals 1 to the sample size. So translated on the right side, right, you can see this is right, this summand from I equals 1 n is 5 here. Is just you're adding up the first height, the second height, the third height, the fourth height, and the fifth height. And then you're dividing by the sample size, which is 5. In here is the sample size. So that's what this summand means here. It's just representing, 2 plus 3 plus 4 plus 1 plus 0.5, just in general. That is for any sample. If I went and got a collected different sample, this still holds. This is still the sample average. Okay. So for example here, right, X bar in this example is 1/5 times 2 plus 3 plus 4 plus 1 plus 0.5. Okay, and this is all represented in this summand here because xi, I've already told you, right? Xi is the height of the ith person. So this is x1, this is x2, this is x3, this is x4, and this is x5 at the bottom. Okay, since x bar equals 2.1, right, there's a little bit of evidence that the height growth might be more than 2 inches. Now the question is 2.1 that much higher than 2? That's where statistical analysis comes into play. So we have mathematical framework to decide, is 2.1 that much more than 2? Because it's otherwise it could be very subjective. What is a sample statistic? A sample statistic is a function of your sample data. So x1 to xn, these are the heights. So the first height, second height, third height, fourth height, fifth height. This is a function g here, and I'll explain. A function just means, right, you probably remember, from high school, you've got this thing fx, and you've got x down here, right? And maybe this thing is quadratic or whatever, and you try to find the roots. You probably remember that kind of thing. This is a function of an x space. Here, your function is going to be a function of all the data points instead, and it's going to output some number on this y-axis. Okay, so that's all this is saying here. It's just a generic function because there's a bunch of different ones we can take. The first one is the sample mean, which is the one we just saw before, where you sum up the x's and then you divide by n. That's a function of your data. You take your data, you plug it in this function, you get a number, right? Take your 5 data points, plug it in, I get 2.1. You're also probably going to be interested in your sample variance. Okay, your sample variance here is a little more complicated, but it's still a sum. So you're summing over for each individual observation. You're going to subtract the mean, then you're going to square that value. Okay, so the first one, right, if I can go back, first one, right, it'd be 2 minus 2.1, which is 0.1, squared that. And you do that for every observation, and then you divide by the sample size minus 1. The geometric mean is also something you might be interested in. It's not something I use, but this is how you use it here. This symbol right here is a product, okay? So what this product means is you're multiplying the observations together. So it'd be the first height times the second height times the third height times the fourth height. So this up here is a sum. This right here is a product. Okay, and you can actually rewrite this thing here in terms of an exponent in the natural log. Don't worry about this that much. This is just an example of another function you might use. We actually won't really use it in this class. But in general, all statistics is you plug your data into some function and you get an output that you can then interpret. So as an example, sample variance. So here we have the heights. Okay, so I have the sample average is 2.1. This is my formula right here. So my n here is 5. So it's going to be 1 over 5 minus 1. I've got to take 2 minus 2.1, square that. Now I go to my next observation, 3 minus 2.1, square that. Now I go to my next observation, 4 minus 2.1, square that. And then I go to my next observation, 1 minus 2.1, square that. And then lastly, I go to this final observation here, which is 0.5 minus 2.1, and I square that. Overall, I get a sample variance of 2.05. This is a geometric mean example. So I'll just briefly walk through this. This is the second way is just an equivalent way to do it. Here, this first one, right, is the product from I equals 1 to n of xi raised to the 1 over n. So that means the 5th root, just so you know. If you have a fraction, if you raise an exponent 1 over a, that's like the 8th square root. So 1 over 2 to the 1 over 2 will be a square root. So I'm going to multiply the heights together. That's what this product says. 2 times 3, that's the second height. That's Jared's height. Times 4, that's Diane's height gain. Times 1, that's Jenny's height gain. Times 0.5, that's Charles's height gain. And I multiply all those together, I get 12. And then I'm going to raise that to the 1 over 5, which is essentially saying, right, so 12 to the 1 over 5 is equal to the 5th root of 12. So you can actually calculate in your calculator. And I get 1.64. The other way to do it is I can use this kind of relationship here. This is equivalent here. So I can take inside, I can take the exponent and take the sum of the logs divided by n. So here's the log of Greg's height, this is the log of Jared's height, this is the log of Diane's height gain, this is the log of Jenny's height gain, this is the log of Charles's height gain. I add them all up and I divide by 5. So that's these here. I end up getting this number, x of 0.5, e to the 0.5, right? That's what it's saying. And then I get 1.64. I get the same answer. Okay, some other statistics. You might want the sample standard deviation, which is just the square root of the variance. So this is a square root here. This is just the same formula for the variance. You also really probably want something like the probability of being larger than a value. So if I want to know what proportion of students have a height bigger than 2 inches, I'll just go and I'll count, okay, how many had a height bigger than 2 inches and average that. So this function here, what is this saying? This is saying the probability of xi bigger than some t. It is 1 over n times the sum of, this is called an indicator function of xi is bigger than t. So an indicator function here does 2 things. It'll evaluate to a 1 if the condition holds, and it'll evaluate to a 0 if the condition doesn't hold. So if a height gain is bigger than t, whatever t is, this indicator function is going to evaluate to 1. Otherwise, it'll evaluate to 0. So if a height gain, if I'm looking at t is 2 and a person's height gain is 3 inches, this indicator function for that person will evaluate to 1. And if they only grew 1 inch, it would evaluate to 0. So we'll just do an example here, the sample standard deviation. This just comes from the other slide here, 2.05 is this variance. I'm just going to plug that in, take the square root, I get 1.43. That's easy. Now, what if I want to estimate the probability that a person grows more than 2 inches? So I'll do that. I'll walk through and compute these indicators. So this is the probability statement here. The probability of xi is bigger than 2 is equal to 1 over n times the sum of these indicators. So I can go through and I can look at all the heights. Greg is not bigger than 2 inches. It's exactly grew 2 inches. So he gets a 0 here. His indicator function evaluates to 0. Jared grew 3 inches, which is bigger than 2 inches, right? So his indicator function evaluates to 1. Diane grew 4 inches, which is bigger than 2 inches. So Diane's indicator function evaluates to 1. Jenny grew 1 inch, which is not bigger than 2 inches. So their indicator function is 0. And lastly, Charles only grew 0.5 inches, which is smaller than 2 inches. So their indicator function also evaluates to 0. So 2 out of the 5 students, thinking about it differently, 2 out of the 5 students had a growth over 2 inches. And then I divide by 5. So 2 out of 5, that's what this is here. And it's 0.4. So this is using an indicator function here. And by the end of this module, you'll have some good kind of understanding of what these are. So again, an indicator function evaluates to 1 if the condition inside the function is met and 0 otherwise. There's many, many ways that you can use an indicator function. For example, I could use an indicator function like this. So this is an indicator function here. It says the indicator of 2 less than xi less than 5. Okay, this function evaluates to 1 if xi is bigger than 2 and less than 5. Otherwise, it'll evaluate to 0. Okay. Now imagine that I have another variable zi. I don't know what zi is. Maybe zi is weight gain, okay, in pounds. So this indicator function here will evaluate to 1 if both the height gain and the weight gain are bigger than 5, as an example. So both of these have to hold. That evaluates to 1. Otherwise, it'll evaluate to 0. This is another example of an indicator function. What if a person's squared height is less than 4? So this would evaluate to 1 if xi is less than 4, or this is an absolute value statement here. So an absolute value statement just means if it's a negative value, you turn it into a positive, basically, if the change here is less than 2. And you can also use an indicator function for categorical variables like yi. So yi here is a categorical variable in this example, right? It's their name, yi. Indicator of yi equals Greg evaluates to 1 if that person is named Greg. Otherwise, it evaluates to 0. Here's some other sample statistics examples. So let's say I want to estimate this probability that a height gain is between 2 and 5 inches. So again, all I need to do is I need to do 1 over the sample size times the sum of these indicator functions. So we'll walk through each one. So 1 over 5, Greg, right, has a height gain of 2 inches. It's not bigger than 2 inches. It's equal to 2 inches, right? So this inequality doesn't hold. So this indicator evaluates to 0. Jared grew 3 inches, which is bigger than 2 inches, but less than 5 inches. So it's in that range. So this indicator is 1. Diane grew 4 inches, which is between 2 and 5. So this indicator is also 1. Jenny grew 1 inch, which is smaller than 2. So it's not in this interval. So this indicator function is 0. And lastly, Charles grew 1/2 inch, which is smaller than 2 here. Right, so Charles's indicator is also 0. So this collectively sums up to 2 over 5. You also could just eyeball this, right? This is the formal math, right? But if you wanted to eyeball this, I can look at it, I can say, okay, 1, 2 out of the 5 had a height gain between 2 and 5 inches. Here's another example. I can compute, this is the probability that xi squared, which is your height gain squared, is less than 4. And this is just going to be 1 over the sample size times the sum of the indicators that xi squared is less than 4. So here I have 1, 5 times, I'm going to actually plug in the values of xi here. The indicator that 4 is less than 4. Why is that 4? Because Greg's height is 2. 2 squared is 4. This evaluates to 0. 4 is not less than 4. 4 is equal to 4. Okay, the second one is 9 is less than 4. This is because Jared's height is 3 inches. Height gain is 3 inches. This indicator evaluates to 1. The next one is the indicator that 16 is less than 4. This is Diane's height gain is 4 inches, so 4 squared is 16. It's not less than 4. This is going to evaluate to 0. Next is the indicator that 1 is less than 4 because Jenny's height is 1 and 1 squared is 1. And lastly is the indicator 0.25 less than 4 because Charles's height is gain is 0.5 inches and 0.5 squared is 0.25. So collectively I have 1 over 5 times 0 plus 0 plus 0 plus 1 plus 1. So it's 2 over 5 here. So probability of a height squared being less than 4 estimated here, this is based on my sample, is 2 over 5, which is what, 40%. Okay, sample percentiles. These are the smallest value of this function such that this holds. Okay, so this is I guess kind of confusing. I'll walk through it in an example, but this is just the math. This is just saying, hey, MP is some number. So MP, right, could be 2, it could be 3, it could be 7. And it's the point where it's the smallest point. That's what this argument means, where this sum, this function here, this probability is bigger than P. So P could be 0.5. What's the value there? So 0.5 here, the 0.5 percentile is the sample median. And you can do this pretty easy in R too. So let's look at an example. So this is an example. What's the 0.3 percentile of this height gain here? Okay, so 0.3 percentile will be the height at which 30% of the data points, at least 30% of the data points, are smaller than that number. That's the definition here. So I can go through and I can look. Okay, if I have a cutoff here between 0 and 0.5, how many students had a height gain less than these numbers here? 0 is the answer. Okay, that's that probability. I'm calculating this function here. If I pick any number between 0.5 and 1, any number between 0.5 and 1, then Charles's height is smaller than that, but none of the other heights are. So this function will evaluate MP, I'm saying. MP is between 0.5 and 1, will be 1/5. If I pick any number between 1 and 2, here, Charles's height is smaller than this, Jenny's height is smaller than this. So this function here will evaluate to 2 over 5. If I pick any number between 2 and 3, Charles's height is smaller than this, Jenny's height is smaller than this, and Greg's height is smaller than this. So 3 out of the 5 students had a height smaller than 2.5, for example, or 2.7. If I pick any number bigger than 3 but smaller than 4, that's 4 out of 5 students have that. And if I pick any number bigger than 4, that's all the students. All the students had a height gain smaller than 4. A number bigger than 4, so smaller than 5. So the 0.3 percentile is going to be the smallest value where the indicator sum is bigger than 0.3. So I can see here, okay, right, 1/5 is 20%, 2/5 is bigger than 30%. So any number in this range between 1 and 2 represents a 0.3 percentile of the sample. The median here is between 2 and 3. Why? Because here we can see this value, 3/5, is bigger than 50%. This value is smaller than 50%. So this is the first time that this sum, this indicator function here, evaluated to that number. Okay, here's another example. We have BMI, body mass index, in patients with dementia. So what levels of BMI in patients are concerning? Well, we can find the 0.1 percentile, which is a measure of really small BMI. Or in our sample, that'll be the point, right, where at least 10% of the sample is smaller than this. So if I look at, right, M1 equals 0.45, if I filled 14.5, if I filled that in right here, only one observation is smaller than this. Well, this is equal to here, greater than or equal to. 2 observations are smaller than this, right? So that would be a 0.1 percentile. What's the median? The median is the point where half of the data points have happened before and half have happened after. The median here is 21.9, because I can see, right, if I use 21.9, there are 10 observations that have a BMI smaller than or equal to 21.9 and 10 that didn't. Another thing I can estimate is what's the probability that a dementia patient has a BMI less than 16.7. I'll just go to less than or equal to. So I'll just go to 16.7. This is it right here. That's 1, 2, 3, 4, 5 patients. So these indicators, right? These indicator functions in the sum will evaluate this sum here. These all evaluate to 1, 1, 2, 3, 4, 5, 6, 5. And these all evaluate to 0. So it'd be 5 out of 20, which is 25%. Which also means that 16.7 is the 25th percentile of your sample. So these probabilities and the percentiles, they kind of work in reverse, right? Okay, our statistical software, it's open source. You can build your own packages and functions. People are adding things to it all the time. It differs from SAS, which has pre-built functions. It's free, so anyone can use a function you write for a paper, and it's reproducible. It allows sharing code with others. So R Studio provides a good interface for using this software. Download these immediately. And if you have problems downloading it, please let me know. So again, right, SAS is something that people use a lot. SAS is a multi-billion-dollar company, whereas our statistical software is free. SAS has marketed their way kind of around the world. And you know, they're offering a service that really isn't even as good as R, which is a free software. So I think that a lot of, you know, academic progress has been halted by SAS and their greed. So this is what our statistical software looks like. You can see here, this is the R Studio. This is what we're going to be using. So up here, you have your code on the top left. You can run your code by clicking this here. Down here, you have this kind of console. This shows the results at the bottom. Up in the top right, you have storage. So these are different things you've stored, maybe your data set. If you store a mean, it'll be up there. And then this bottom right window contains files. It's also has plots. You see this plots tab. It also has help here. So let's look at the 2 example data sets. So I have 2 data sets here, M1L1 D1.csv, M1L1 D2.csv, and M1L1 code.csv. And you're going to save them and put them in the same file so we can source them into R. So let me just show you where these are. If I go to the resources, should have these up here, I think. Did I not have them up here? Okay. Okay, for some reason I do not have these up here. I do have them here. So I'll go ahead and upload these right now. M1D1 and M1D2. So I just want everybody to see, I'll upload these I'll upload these right after I get off of this to the module 1 resources, put them here, and you can download them. But what you're going to want to do is you're going to want to download these things and put them in the same folder here. So here I have, these are my 2 files. This is what M1L1 looks like. It's actually just the heights here. And this is what M1L1D2 looks like. It's just the BMI data. That's it. So you're going to save these in the same folder. And you're also going to save this M1L1 code here as well. Okay. So let's kind of work through this, and then the lecture itself, and then I'll kind of hop back in here again and we'll go through things. Okay. So you're going to save these all as the same file in the same folder. Notice I have everything all in the same folder here. So you'll download, once I upload these files, you'll download them and save them. Okay, there's a lot of code here. I have get WD. I can list files. These are the files that I have there. The data is not in this folder, so I need to find where it is. So, how I do that, I can just show you here. So this is the data set. This is the first code that we do have online right now. And I can look and see what directory I'm in right here. This tells me here. So, hey, I'm in this lab cutoffs directory. What I really want to do is I want to find this folder here. So this is my folder here. I can go right click on this and go to properties. So in properties, right, I can see this is my file destination here. And I want to basically tell R, hey, look, I want to go to this. So I can add that here. So when you copy paste it, if you're on Windows, right, it's going to have these backslashes. What you need to do is you actually need to come through and turn them into forward slashes. That's just the syntax here. So here I have my forward slashes. And then you need to put quotation marks around it. So if I put quotation marks around it, so first list.files will show me what are the files in my working directory. So I'll copy paste this into something called setwd, which is saying, hey, look, I want to change my working directory to be this now. You also want to put a backslash at the end. So here I can adjust it. Here now I've changed my working directory. I can even check in the bottom. So I want everybody to be clear, right? You can run things from the top. Notice how I click this run button. I can also do that in the bottom, right? So I can click get WD up here, but I can also just come into my bottom console and type in get WD. The way to think about it is basically this is like your saved Word file. This is there. And if I want to do like things on the fly, like, oh, I don't know what 2 + 3 is, I can figure that out on the bottom of my console here. So now that I'm in here, maybe I want to know what files I have. So I can click list files. Again, I'm clicking this run button up here. Everybody see this run button at the top. If I want to run multiple things at once, I can highlight all of them and click run. So it's really nice. So what are my files? And I can also do this in the console, list.files. So these are going to be all the files in my working directory. I can see I have M1L1D1, which is this file right here. I actually have that in my working directory now, which means I can load it. So here's how you read data. Now I want to point out something first. You'll notice that these are all CSV files. So a CSV file is just a special type of Excel file. It's actually really easy to adjust. Like if I go to Excel here and I have an Excel file and I want to save it as a CSV, you'll just go save as, I'll save it wherever, doesn't matter. It's OBGYN, for example. And you just come right here, you see this drop down, you'll just go down to CSV. I'll call it book 1. The reason you do that is sometimes I've had trouble with reading in Excel files directly. It still looks like an Excel file, right? A CSV file. Just make sure you save those as that. So I'm going to read in the data. This is a function. And I'm saying, hey, look, I want to read in M1L1D1.csv. And I can copy that right here too. So R is case sensitive, right? Which means it needs to be spelled exactly. if it has a lowercase letter and it's all uppercases, it won't work. So I'm going to read in my data. So now I have my data. Here it is. This is my data. And you can see now it's popped up into my environment at the top. It's 5 observations with 3 variables. I can actually click on it and look at it. See, this is my data right here. Now, one command that you probably want to use is head. So head just gives you the names of the variables and the first couple of rows here. So here I can look at header. I have these are my I's, observations. I have my names. This is my Y1s, Y1, Y2, Y3, Y4, Y5, and these are my height gains. I can also index these things. So if you look at the console in the bottom, notice whenever I type in data, see how it pops up? I can actually just print out my whole data set if you want. The other thing I can do is I can index the I column like this, data $. See how it pops up a menu at the bottom? So I can get the I's, these are just the observation numbers. I can get the names of the students, these are their names. And I can also get the height gains of the students, height.gain. So I can actually index each of the columns specifically by using the $. And that's what you're going to be doing anytime that you're working with a data set. So that means it needs to be in this kind of structure here, where you have, right, column name, observation, information, column name, information, column name, information. And I can also get the names of my columns like that if I forget. I can also index different things. So maybe if I want to know what is the first student's name, all I have to do is add this bracket to the end, bracket 1. So I can say, okay, what's the first student's name? It's Greg. If I say just data name, it'll print out all of them. What's the second student's name? That's this here. So I have a bracket, number 2. What's the third student's name? Or what's the second student's height gain? Is 3 inches. I can also index multiple entries at the same time using this C thing here. So C just makes it a vector. So C here, I can put things together. You have to separate them by comma. So what I'm asking R to do here is, hey, tell me what the height gain of the 2nd, 3rd, and 5th students are. So you can use this syntax here like this. Oh, and I see, oh, these are 3, 4, and 0.5. And if I actually look at my data, right, this should be able to correspond with that. So I have, 3 here, 4 and 0.5. The second observation is 0.3. The third observation is 4. And the last observation here, the 5th one is 0.5. So that's how you index multiple things at the same time. The other thing you can do is with the data itself, you can index rows and columns. So if you want to look at one observation or one column specifically, instead of naming them, you can use, instead of brackets like this, you can use brackets with commas. Now this is going to give me an error here because this is not what we call a matrix. Data here, the actual data frame itself, you can see is a matrix, right? It has rows and it has columns. So it needs to look like that. Whereas if I look at data height gain, if I just look at that column, it's not a matrix. It's just those values. So I'm going to need to index the height in the way that I'm doing before. But here I can index, this would be the first observation, completely the first row data. You can see that prints out, hey, the first student was named Greg and they had a height gain of 2. I can also look at the first column of data, which are our observations. Sorry, it'd be like comma 1, like this, 1, 2, 3, 4, 5. So I think it's easier to index like this, name, data, height gain, that kind of thing. But that can be useful. You also might want to know what's the dimensions of your data frame. So there is no dimensions of height gain because it's not a matrix, but you will get dimensions of your data. This tells me I have 5 rows and I have 3 columns. That's what this tells me. And you can actually see that, right? I have 1, 2, 3, 4, 5 rows and 1, 2, 3 columns. This is just kind of an added thing from R. I can also look at some other basic functions would be like the length. So this is the length of the height gain is 5, which means there's 5 observations here. You can also look at how many rows in the data by typing in row of data. I can also look at how many columns in the data by typing in col of data. Another thing that I probably want to use is use functions. So we'll go through a lot of these functions throughout, but the basic one would be mean. Okay, what's the mean height gain? See this function right here? I have mean, and then I wrap it around in parentheses. Oh, the mean height gain is 2.1. I can also calculate it like this, right? Because the definition of a mean is, this here. I can calculate this directly by taking the sum of the values and dividing by the overall length of the data, which is n, by doing it like this. So this is saying, hey, look, take the sum of the height gain and divide by the length of the height gain. I can run that, 2.1. I get the same thing. I can get the variance in a similar way by just plugging into var. So var of this, 2.05. I can also calculate the formula directly. So what is the formula? You see the formula is right here. It's the sum of each observation minus the sample average squared, and then divided by the sample size minus 1. So that's this here. So you see I have it all wrapped up. Now be careful. You want to be careful about your parentheses here. One of the nice things about RStudio is notice whenever I pass over this parentheses right here. Do you see on the right side how this lights up? That's telling me that these two parentheses are paired up. Likewise, whenever I step right here, you can see this here. I have data height gain. I'm taking the mean of the data height gain. I'm subtracting it. So that's what these are doing here. And then I'm squaring it. And then I'm summing it. So I can even run just this part right here if I want, which is going to basically take, okay, if I look at the data, right, what's the mean of data height gain again, just to show you, and data height gain. So this first observation is 2 minus 2.1 squared. So 0.1 squared is 0.01. See this? Come up to the top. The second observation will be 3 minus 2.1, which is 0.9 squared. 0.81. See that there? Next observation will be 4 minus 2.1 squared. 4 minus 2.1 is what? 1.9. 3.61, and et cetera, et cetera. And then I'm just summing that up. So I'm wrapping the sum around it. So here, this is my sum of squares, 8.2. And then onto the bottom, I'm going to divide by the length of the data minus 1. You can see that here. Now, notice I have everything in parentheses. You want to be really careful about parentheses, right? If I did like this, for example, if I didn't have this parentheses on the bottom, and I did like this, this is going to give me a different answer, 0.64. Why? Because what it's doing is it's dividing by just this number here, the length, the n, and then it's subtracting 1. You don't want to do that. That's a boo-boo. I can calculate the proportion bigger than 2, just like we just did. Okay, I've got data height gain, and this is just going to calculate the indicator function here. So you'll see when I run this, it's going to spit out falses, trues, falses, and trues. Let's actually look at the data height gain. So everybody see me on the bottom. So I see, right, this first one, what this is telling me is false. It's not true. That is bigger than 2. True, it is bigger than 2, 3. True, 4 is bigger than 2. False, 1 is not bigger than 2. False, 0.5 is not bigger than 2. I can see all that right there. Okay, so these trues and falses, the way that R deals with them is it treats a true as a 1 and a false as a 0. So it's literally doing those indicator functions that we just walked through. And I can take the mean of them then. So the mean of these will be that proportion, 0.4 here, which is the same thing we got before, right? It was 4 over 2 here, where I have this. It's 2 over 5, which is 0.4. So it calculates that for me directly. I can also calculate this other function, right? What's the proportion of the xi's less than 4 squared? First thing I'll do is square all these. So just show you what this looks like. See how I'm highlighting things and I can run different portions of it. Then I see it in the bottom. So these are all those values squared, right? 2 squared is 4, 3 squared is 9, 4 squared is 16, 1 squared is 1, 0.5 squared is 0.25. And this is going to actually take this and turn it into a logical statement. So these are going to be the indicator functions. False, 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 true, true. And then I take the mean of those. And I end up getting 0.4 again. Let's say I want to get the proportion between 2 and 5. So how do I do that? I have to add this and condition here. So what it's going to do is this is going to turn into a set of logical statements here. False, true, 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 false. These are the ones bigger than 2. Let me just pull up the heights again, data height gain. Run through, false, true, true, false, false. Okay, and then this one here, this is gonna be less than 5. I have true, 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 they're all true. And then what this is gonna do is this is gonna check this and is gonna check both conditions. So with both conditions, right, I get a false, true, true, false, false. And I can take the mean here, 0.4. I can also get quantiles. So quantile, right, I have the data height gain. I can take the 0.1 quantile, that's what this is doing here. And if I ever forget how to use a function, the easiest thing to do is you can come in here and you can type in help, mean. So I'll look at mean. Oh, wow, it tells me how to use it. Say, hey, this gives you the mean. Okay, you plug in something. What are the arguments? I'm plugging in X, it's gonna be a data, and then I get out a number. And these are examples here. So I can always go to a help function and just run this to give you, some numbers, things like that. These will always give you kind of examples. So this quantile function, if I look at it, help quantile, this is how you get percentiles. These are the sample quantiles. What do I have to feed in? I have to feed in X, which is a vector. I have to feed in probs, which is my P. So here I have this here, and I don't know what type equals 1 is. You don't necessarily need that. So this is going to give me my 0.5. My 0.1 quantile is 0.5. My 0.25 quantile is 1, right? Because why is it that? If I look at height gain and I'm at 1, then 2 students had a height gain less than or equal to 1 out of 5, right? So that's 40%. I can get the median using this 0.5 right here, quantile, and I can also just type in median, right? This is another function. So I can type in help, median. If you ever have problems, right, I can look things up, compute the sample median, and then plug in the values. And this is just saying here, right, these are just the different values you can use. If I look at help quantile, one of the things that you can do to kind of help you understand functions is you see in this help file, if you go all the way to the bottom, what you get is you get some examples that you can use, that you can run. So that's these right here. You can see, hey, look, I've got these right here. I can just plug these in, right? So here I've got, hey, I'm running these numbers, and these will give you multiple quantiles. So they give you examples on how to use the functions. I think it's worthwhile to look at them and test them out. So yeah, what I would encourage you to do is to actually walk through that, download everything, put it into the same folder, go to that folder, upload the data set, and just walk through what we walked through today and try to get an understanding of what was done. So I have the lectures here, just kind of walking through it again. These are things we did. We moved throughout. Hey, I copied this. I replaced the slashes. That gives me the data set now. These were the files that I had at the time when I made this. This is my header. So these are the functions. I have it explicitly set WD used to change the directory, list.files used to see the files in directory, read.csv reads in CSV files, and header looks at the first few rows of data. Just gives you an idea what the data looks like. I can use a $sign to index columns. So here I'm indexing I'm indexing the name, I'm indexing the height gain. I can use bracket K to index the kth element of these vectors. The first student's name is Greg, second student's name is Jared, second student's height gain is 3. I can use C here to index multiple entries. You really won't have to use that in this class, but just to show you, hey, I'm grabbing the 2, the 3rd, and the 5th entry. Again, right, this is how you index rows here. So if I want the first row, I just do, right, data of 1. How do I know it's a matrix? I can use the dimension. So what is a matrix? Just walking through it. These are matrices. This is how it looks like. It looks like a data frame. Any Excel data set that you've seen is a matrix. A vector is just one row of the data frame or one column of the data frame. So this, right, don't worry about the math, but this, right, looks like an Excel file. This looks like a row. So I can use length to get the length of a vector. I can get the rows, number of rows of a matrix using in row, and I can get the number of columns of a matrix using in col here. So the length, the row, columns. Functions, I can use functions here. The means of the height changes, these are the means of the height changes. I can also calculate that directly. I can also do the variances of the height changes. And then I can look at what proportion is bigger than 2. So we walk through this in R. It's the mean of this indicator function here. This is calculating other things, right? This is the probability that xi squared is less than 4. We just saw this, right? And just square it, check it's less than 4, it turns it into logical statements, and I take the mean, I get 0.4. This is the probability that xi is bigger than 2 and less than 5. You can see that here. Data height gain is bigger than 2, data height gain is less than 5. This uses and, which is an and statement. Some other functions, what about quantiles? You can use the quantile function. So here's this quantile function again, right? I'm plugging in the data height gain. I want the 0.1 quantile or the 0.1 percentile. I plug in data height gain. I want the 0.25 percentile. I want the data height gain. I put in the 0.5 percentile. And this is my median as well. So this just gets you the same way to get the median using type equals 1. And again, your help menu tells you a lot of really important stuff. So the top part, the description, tells you what the function does. The function gives you sample quantiles. Smallest observation corresponds to the probability of 0, largest to probability of 1. This is the syntax of how you use the function. Then these are the arguments, what goes in the function. So right, if you look at this function here, I have in here 1, 2, 3 arguments. There are actually way more arguments you can give in here if you want, but you don't necessarily need to. And then you have examples at the bottom, so you can copy and run, or you can type in example. So I can even come here and type in, example mean, for example, and it'll actually print out the means. These are the examples here that I ran. You might see this kind of thing online. This is just saying, less. This is not saying less than or equal to. This is just assigning equals to. And then you can test functions. So I want to kind of walk into the first quiz. That's going to be due by the end of this next week, or the end of this week. So it is a academic, it's a requirement to do this, so AEA. So you go to the quiz, I'll let you preview the quiz, just give you an idea. So I want you to actually do these solutions. Okay, so this is what's the sum of the xi squared for these values are 1, 3, 5, 7, 2, and 1. So this is related to just doing the math, right? This kind of math that we did before, where we added things up, we used indicator functions, those kind of things. Second question, this is what's the 0.2 quantile of this here? You can actually use R too if you want, but you'll find the point where the probability of being smaller than or equal to that value is less than, is 0.2, at least. What's the mean of this data here? What's the solution to this function? So this is the sum of the indicator function of xi squared plus 2xi being bigger than 10. So you probably need to calculate xi squared plus 2xi for each of these observations first, check whether they're bigger than 10, and then add it up. And you can use R if you want, that's fine. Or you can do it by hand. What's the median of these values here? And then that's the end. So that's the quiz. Please do that as soon as possible. It'll actually be due by the end of this weekend. So it should be due by Sunday night. All right, well, please, let me know if you have questions. I actually do have office hours this first week. So if you have any issues, please come by and talk to me. I personally think that kind of the synchronous version where I actually interact with you as I go through this is a lot more efficient. So if you value that as well, you can use the office hours for that. All right, that's the end of module 1.